Optical activity and chirality. Let us discuss how optical activity is related with chirality. An object is said to be chiral when its mirror image is not superimposable on it. It's not superimposable on it. That means the object do not possess any symmetry. There is no symmetry in the molecule. So we can classify these chiral molecules as dissymmetric molecules. These are dissymmetric molecules. And the object along with the non-superimposable mirror image is known as optical isomers. Optical isomers. Our hands, our left and right hands are examples of chiral object. Left and right hands are appears as mirror images. If we put one over another, it will not superimpose. So it is chiral. Same way, the English alphabets P and its mirror image are optical isomers and that are chiral. This is the object and this is the mirror image. If we place the mirror image over the object, this will be appear like this. That is, the mirror image of P is not superimposable on the object P. So this is not superimposable, Hence, it is considered as chiral. Same way, if we consider O, the mirror image appears like this and the image is superimposable on the object and it is a achiral object. The concept chirality is always associated with the symmetry of an object. That is, if a molecule or an object is symmetric, then it is considered as achiral. If a molecule or an object is dissymmetric, then it is chiral. So, before going to the details of chirality, we should have a thorough idea about symmetry and the elements used to find out symmetry of a molecule. So, let us go to the details of elements of symmetry. Elements of symmetry in the sense, these are the geometrical entities which are used to find out the symmetry of a particular molecule. Geometrical entities which are used to find out symmetry of a molecule. These may be a line, it may be plane or a point, etc. So, the major elements of symmetry used are, one is center of symmetry. The second one is plane of symmetry. Then third one is axis of symmetry. Then the fourth one is alternating axis of symmetry. The first one is center of symmetry. We can define center of symmetry as like this. This is an imaginary point in a molecule and a straight line which is passing through it will meet identical groups or atoms at equal distance from the point in the opposite directions. So to make it clear, consider an example. Here I am going to take ethene. The structure of ethene is like this. If you consider an imaginary point at the center of double bonds, and if we draw a line which is passing through this point, at equal distance from this point in opposite direction, we can meet two hydrogens. That is, these two hydrogens are identical. Same way, here also, we can meet two identical groups in opposite direction at equal distance from this point. So, this molecule has a center of symmetry. Okay, look at this three-dimensional model. This is a planar molecule. So, imagine there is a point at the middle of the double bond, and if we travel equal distance from that point in opposite direction, we can meet the two red atoms. Same way, the two green atoms are equal distance from that point. So this molecule contains a center of symmetry. The next element is axis of symmetry. It is an axis around which a rotation by results in a molecule indistinguishable from the original one. So, axis of symmetry means consider a molecule, that is, for example, consider water molecule. The shape of water molecule is bent. The structure of water is like this. Imagine this molecule is lying on this paper. If I am drawing a line which is passing through oxygen, which is lying on the same plane, and I am going to rotate this line in a clockwise direction. After rotating 180 degree, I'll get the same molecule, or I'll get the same structure like the first one. That is, if I'm mark this hydrogen as 1 and this hydrogen as 2, both are hydrogen, both are identical groups. If I'm rotating 180 degree, this molecule will be appear like this, and this hydrogen 1 will be here and the hydrogen 2 will be here. But if you look at the structure of these two structures are identical. The second one is also looks same as that of the first one. But the molecule is interchanged. Actually, this is the original one and this is the rotated one, but the rotated structure is also look like the original one. So, the operation I did here is the rotation, and the rotation is done through this axis. So that means this molecule possesses an axis of symmetry. Here is a three-dimensional model of water molecule. Okay, if you rotate this molecule 180 degree like this, we'll get a molecule which is identical to the original one. But that is not the same one. If we rotate again 180 degree, that is the original one. So here, after rotating 180 degree, we will get a structure which is indistinguishable from the original one. Okay, the next one is plane of symmetry. Plane of symmetry means a plane which divides the molecule into two identical halves or two equal halves. So, consider an example CH2Cl2. So, if we draw the structure, this will be like this, Cl, Cl, and we can draw this by using dash and wedge projection. So, H. Imagine a plane which is passing through these three atoms. That is a plane which is passing through hydrogen, this hydrogen, this hydrogen, and this carbon. So, this plane divides this molecule into two equal halves. So, we can say this molecule contains a plane of symmetry. Here's a three-dimensional model of dichloromethane. Two white-colored atoms represent hydrogen, gray is carbon, and the two green-colored ones are chlorines. So if we draw a plane which is passing through two hydrogens, that is two white-colored one and carbon, which produce two identical halves. Same way, if we pass a plane through carbon and two chlorines, that also produce two identical halves. The next one is alternating axis of symmetry. A molecule possesses an alternating axis of symmetry when rotation about an axis followed by reflection through a plane which is perpendicular to the axis of symmetry produces an indistinguishable structure with the original. So, consider an example trans 1,2-dichloroethylene. The structure is like this, C double bond C trans. So, two chlorines are in trans position and hydrogen. So, first of all, we have to rotate this molecule in a particular angle. So, I'm going to rotate this molecule through this plane. So, through this plane, I'm going to rotate this molecule in 180 degree. So, this molecule will be appear like this. C double bond C. This Cl will come here and the hydrogen will come here. Same way, this chlorine appears here and the hydrogen will be here. The next process we have to do is to reflect this molecule through a plane which is perpendicular to this axis. So, perpendicular to this axis means it is cut like this. So, we have to consider a line passing through these two double bonds. So, if we cut this molecule or if we draw the mirror image of this molecule, resulting structure will be like this. C double bond, this chlorine will come here, this hydrogen goes there. Same way this hydrogen come here and the chlorine goes there. So, the final structure obtained is this. And if we compare this final structure with the original one, this is identical to the original one. And we can say this molecule possesses an alternating axis of symmetry. The first step, we done rotation through an axis, and in the second step, we reflect the molecule through a plane which is perpendicular to this axis. Finally, we get a molecule and its structure is similar to the original one. Now, what about the chirality of organic molecules? Yeah, like we already said, organic molecule is also chiral when its mirror image is not superimposable on it. Let us take an example. This carbon is said to be chiral because this carbon, this tetravalent carbon is attached to 4 different groups. Here, if we look at this example, we can clearly say that this molecule do not possess any elements of symmetry. And the carbon which is attached to 4 different groups or the center carbon is called chiral carbon. Chiral carbon. Or we can also call it as asymmetric carbon. Asymmetric carbon. Or we can call it as, or we can call the center carbon as a stereogenic. It is a stereogenic sender. Stereogenic sender. Usually it is represented by using the asterisk. Let us discuss the criteria which are determining the chirality of a molecule. Certainly, the first one is stereogenic sender. Organic molecule is said to be chiral when it possesses at least one stereogenic sender. So, the next factor is dissymmetry. The molecule should be dissymmetric. Dissymmetric means a molecule which do not possess a plane of symmetry is called dissymmetric. Dissymmetry means there is no plane of symmetry. Plane of symmetry. Now, obviously, a question will be arise here, that is, what is the difference between asymmetry and dissymmetry? If a molecule does not possess any element of symmetry, then that molecule is known as asymmetry. That is, no element of symmetry. No element of symmetry. While dissymmetric means a molecule does not possess a plane of symmetry. There is no plane of symmetry. So, asymmetric means no element of symmetry, but dissymmetric means no plane of symmetry. So, we can say all asymmetric molecules are dissymmetric, but the reverse is not true. Okay. There are so many molecules which possess more than one stereogenic center. Okay, lactic acid is a molecule which having one stereogenic center. The structure is this H, CH3 and OH. This is lactic acid, and here lactic acid have one stereogenic center. Coming to tartaric acid, the structure is like this. COOH, one COOH group is there, one OH group is there, one OH is here, one H here, one H. This is the structure of tartaric acid. If you count the number of stereogenic centers, one stereogenic center is here and one is here. The other two carbons are not asymmetric. Then, if we look at this example, COOH, CH2OH, OH, 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 H. Okay, here the number of stereogenic centers are 3. Actually, 5 carbons are there, but these 2 carbons are not stereogenic. There are so many molecules having more than 3 stereogenic centers also. But if you observe these molecules, all these molecules are not chiral. Some of these molecules are achiral also. For example, this molecule, lactic acid containing one stereogenic center, and it is asymmetric and it is a chiral molecule. It is chiral. But in the case of tartaric acid, even though 2 stereogenic centers are there, but it is achiral. It is achiral. Because if we draw a plane which is passing through this bond, that is a plane which is cutting this bond, the 2 halves formed here are identical. So, there is a plane of symmetry, and we cannot call this molecule as a dissymmetric molecule, and hence we can categorize this as achiral. Even though there is a stereogenic center, the molecule should possess a dissymmetric center, then only it become chiral. Okay, we learned all the factors about chirality, but there is an interesting thing is that there are some molecules which do not possess any stereogenic centers, but they act as chiral. So, in some molecules, there are some molecule there is no stereogenic center, but they act as chiral molecule. Some examples are, one is allene, and the next one is suitably substituted biphenyl system. Suitably substituted biphenyl system. The first one is allene. This is allene. This is the basic structure of an allene. So if you substitute a CH3 group here, in same way this H is replaced by one CH3 group, then this molecule is chiral. By simply looking, we'll think this is an achiral molecule because we'll think there is a plane of symmetry. But actually this molecule does not possess any plane of symmetry. Here, these two groups are lying on the plane, and this group is projecting towards us and this one is projecting backwards. This is the structure of allene system. This is the basic structure. From this structure it is clear that if we replace hydrogen and substitute any other group, the molecule formed is a chiral molecule. If we draw a plane which is passing through, if we draw a plane which is lying on this plane, that plane will contain these three carbon atoms and this CH3 and this hydrogen, but these two molecules do not lying on this plane. That means one of the hydrogen is projecting here towards us and one is projecting backwards. So we can observe an asymmetry there. So this molecule is chiral. The next one is suitably substituted biphenyl system. Like allene, this is the biphenyl system. Actually, biphenyl system is achiral, but suitably substituted biphenyl system is chiral. We have to think that is one of the benzene ring is lying on the plane and the next one is perpendicular to this plane. That is, this is projecting towards us and this is projecting backwards. That is one these two benzene rings are perpendicular to each other. It is clear from this three-dimensional model that these two phenyl rings are perpendicular to each other. Now here is a plane of symmetry, but suitably substituted benzene rings will not have any plane of symmetry. So if we substitute any groups here, I am going to substitute a COOH group and here I am going to substitute one NO2 group. Same way I am going to substitute an NO2 group here and one COOH group here. Actually, this molecule does not possess any plane of symmetry because if you draw a plane which is passing through this molecule, this plane is completely containing this benzene ring and COOH and NO2 groups, but it is passing through the middle of the second phenyl ring system. But the two groups substituted in ortho positions are different. So this will not cut the molecule into two identical halves. And this is a chiral system. So this is all about the chiral systems without having a stereogenic center.